Good morning, or whatever time it is that you're watching this. I will break the lesson for November 8th down into two videos. So we'll start with section 2.1, operations with matrices. Please keep in mind that all of these operations are to be done without a calculator unless otherwise noted. We'll start with matrix addition. To add or subtract matrices, the dimensions must be the same. In other words, the matrices must be configured the same way, 2 rows, 2 columns, or 3 rows, 3 columns. The dimensions are given rows first, so this one has 2 rows, and columns second, 2 columns. So each of these matrices have the same dimensions. If that's in place, then it's a matter of adding or subtracting corresponding elements. -1 plus 1, 2 plus 3, 0 plus -1, 1 plus 2. In the second example, you see that the first matrix has 3 rows and 3 columns, whereas the second matrix has 3 rows and 1 column. The dimensions are not compatible, so the matrices cannot be added. So again, to reiterate, to add or subtract matrices, the dimensions must be the same. Scalar multiplication allows us to multiply a particular matrix by some scalar, some number. It's kind of like using the distributive property. So for example, given matrix A, to find 3 times A, we're simply multiplying each element in matrix A by the scalar 3. And that would give us the matrix with the same dimensions, 3 times 1, 3 times 4, 3 times -2, 3 times 3, 3 times 0, 3 times 1, 3 times 5, 3 times 5 again, and 3 times -2. So that's the matrix 3 times A. Negative B means to distribute or multiply the scalar -1 by B. So negative B, we're going to multiply each element by a -1. And so we would get the matrix, same dimensions, -1 times 2, -1 times 0, -1 times 1 completes the first row, -1 times -4, -1 times 3, -1 times 2, and then finishing out the bottom row, multiplying each by -1. Then to find 3 times A minus B, we're combining the addition or subtraction that was covered on the first slide along with the scalar multiplication. This matrix represents 3 times A, and this matrix represents -B. So I can find 3A minus B by adding those two matrices. This one is 3A and this one is -B. So therefore, 3A minus B would be the matrix 3 plus -2, 12 plus 0, -6 plus -1, 9 plus 4, 0 plus -3, 3 plus negative 2, 15 plus 1, 15 plus negative 2, negative 6 plus negative 3. The next example just illustrates the notation for identifying an element in a matrix. To find C sub 2, 3 means to find the element located in row 2, column 3 of matrix C. C is the matrix 2A plus 3B. Well, we really don't need to find the entire matrix C. We just are looking for one particular element. So if we go to the second row, third column of A, second row, third column of matrix A, and also the second row, third column of matrix B, we get the numbers 1 and 2. So C will be 2 times 1 plus 3 times 2, which is 2 plus 6, or 8. That's not C, that's C sub 2, 3. The element in the second row, third column of matrix C. Next, suppose we're given matrices and asked to solve for x, y, and z in the matrix equation. Order of operations. On the right-hand side, we have a scalar to multiply by each matrix. On the left-hand side, we have a scalar to multiply by the matrix. So I'll do that first, so that my left-hand side becomes 4x, 4y, 4z, and negative 4. On the right-hand side, just doing it in 2 steps, I'll first multiply each scalar by 2. And then, continuing on the right-hand side, I'll add the 2 matrices. Adding corresponding elements, I have 2y plus 8 for the first element in the first row, 2z plus 2x completes the first row, negative 2x plus 10, and 2 minus 2x. If the matrices are equal, that means that each element of one is equal to the corresponding element of the other. In other words, the element in the first row, first column on the left-hand side is equal to the element in the first row, first column of the right-hand side. So that gives me 4x equals 2y plus 8. Also, the first element in the second element in the first row on the left is equal to the corresponding element on the right. And finish out the bottom row in a similar manner. then you should be able to work backwards from some of these equations and find x, y, and z. I see in this equation, I can immediately solve for x by subtracting 2 and divide by -2. Once I have x, then I can go to this equation and find z, plugging in 3 for x. So I have 4z equals -2 times 3 plus 10, or 4z equals 4, so z is 1. And I can also find y using the answer that I have for x. So I have 4 times 3 equals 2y plus 8. 12 equals 2y plus 8. 2y equals 4, so y equals 2. And I could check using that last equation just to make sure everything worked out properly. 4 times 2 is supposed to be equal to 2 times z, which is 1, plus 2 times 3, which is x. 8 equals 2 plus 6. Looks good. So my answers are x equals 3, y equals 2, and z equals 1. And there's really no system there. Just start in an order to find something and then jump around until you find all values. So that pretty much is the focus of addition and subtraction, scalar multiplication of matrices. Multiplication of two matrices is a different matter. I'm starting out with an example here of a situation where matrices are used. This table represents sales at a football stadium for a given day, and showing the 3 different concession stands and the items that are sold at each one. We have the price for each item and the number of items sold at each stand. So if I wanted to determine how much money the South stand took in, I would multiply the number of bags of peanuts by the price for peanuts, plus the number of hot dogs times the price per hot dog, and the number of sodas sold times the price per soda. And multiplying and adding those numbers together would tell me the amount that the South stand took in, which comes out to be $1,828.75. So if you notice there, what we're doing is we're multiplying this row by this column, pairing off the elements one by one. Peanuts times the price of peanuts, plus hot dogs times the price of hot dogs, plus sodas times the price of sodas. Below that matrix, I've written a similar matrix, actually an identical matrix, without the item labels. 120, 250, 305 represents the number of peanuts, hot dogs, and sodas sold, respectively, at the South stand. And this matrix represents the price for each of those items. So in order to find the amount of money taken in at that football game at all 3 stands on that given day, I would multiply row by column, row by column, and row by column, and add those three together. And that would give me the total amount taken in that day. Notice that this matrix has 3 rows and 3 columns. This matrix has 3 rows and 1 column. The dimensions are not the same, yet they are compatible for matrix multiplication. In order to multiply matrices, the number of columns of the first matrix must be the same as the number of rows in the second matrix. And the product will be given by the number of rows of the first matrix and the number of columns in the second matrix. So when we do this matrix multiplication, we're going to get the amount taken in at each concession stand on that given day. And then to get the total amount for the day, you'd simply add those numbers together. Well, let's look at a similar example with more reasonable numbers that we can more easily multiply in our head. So I have 2 matrices with the indicated operation multiplication. First, I want to check to make sure that the multiplication can be done. The first matrix has 3 rows and 2 columns. The second matrix has 2 rows and 2 columns. So I can multiply the matrices. The resulting matrix is going to have 3 rows and 2 columns. That's good to know so that you can configure it properly when you're writing the answer down. So we start by multiplying the first row by the first column. And I'll write this step down the first time. Normally we can do a lot of this in our head and not have to write down so much. So it's -1 times -3 plus 3 times -4. And now I multiply the first row by the second column, and that will complete my top row. So I have -1 times 2 plus 3 times 1. It's the first element times the first element plus the second element times the second element. Do that with each additional row. So on the second row, hang on, I have all of my pens in the wrong slot. Okay, the second row, I have 4 times -3 plus -2 times -4, and 4 times 2 plus -2 times 1. Third row, I have 5 times -3 plus 0 times -4, and 5 times 2 plus 0 times 1. And if you'll take a second to look at the matrices, the way they're configured, notice that these numbers represent the column, first column. These numbers represent the second column. And the ones that I didn't highlight represent the rows. Or I guess I could highlight a different color. This is row 1. So I'm multiplying row 1. Oh dear, no, I highlighted the wrong thing. Okay. Let's try that again. Row 1 by column 1. That's all for the highlighting. And then we'll do the arithmetic. So 3 plus negative 12. Negative 2 plus 3. Negative 12 plus 8. 8 plus negative 2. Negative 15 plus 0. 10 plus 0. So my final answer is negative 9, 1, negative 4, 6, negative 15, 10. A 3 by 2 matrix as expected. In the next example, I have a matrix with 2 rows and 3 columns. I'm multiplying it by a matrix with 3 rows and 3 columns. The multiplication can be done. This time, I will have a 2 by 3 matrix. 2 rows. Rows go across, 3 columns. Columns are vertical. So, row time column. 1 times negative 2 plus 0 times 1 plus 3 times negative 1. And this is not going to fit the way I'm doing it. So let me try again here. One times negative 2 plus 0 times 1 plus 3 times negative 1. That's the first row times the first column. First row times the second column. 1 times 4 plus 0 times 0 plus 3 times 1. And then the third row, the first row times the third column. 3 times 2 plus 1 times 2 plus 0 times 0 plus 3 times negative 1. Bottom row, 2 times negative 2 plus negative 1 times 1 plus negative 2 times negative 1. Bottom row times second column. First element times the first element plus the second times the second plus the third times the third. And then the second row times the third column. First element, second, second, third, third. So you have 2, 0, and negative 3, 4, 0, and 3, 2, 0, and negative 3, negative 4, negative 1, and 2, so negative 5 and 2, 8, 0, and negative 2, 4, 0, and 2. And I'm not sure about my first element here. Let me double check this one. I need you here. I found my mistake. This was supposed to have been 1 times negative 2. So negative 2 plus 0 plus negative 3 will make this a negative 5. Okay, so that should be correct. All right, another matrix multiplication. Here I have a matrix with 1 row, 3 columns. Here I have a matrix with 3 rows and 1 column. So the resulting matrix should be a 1 row, 1 column number. I multiply the first element by the first, the second by the second, the third by the third, and add together. So it is 1 times 2 plus negative 2 times negative 1 plus negative 3 times 1. So my 1 by 1 matrix is 1. The last matrix, I have a matrix with 3 rows, 1 column, and a matrix with 1 row, 3 columns. So this one should be a 3 by 3. I will get the first row by multiplying the first row by the first column. I get the second row multiplying, I get the second element on the first row multiplying the first row by the second column. Completing the top row, first element times the third column. The second row is gotten by multiplying the second row by each column individually. And same thing with the bottom row. 1 times 1, 1 times negative 2, 1 times negative 3. All right, and we'll end with solving a matrix equation for A, B, C, and D. We did this on the addition aspect, but these matrices are being multiplied on the left-hand side. So order of operations, I have to do that first. Multiply the first row by the first column. So I have 1 times A plus 2 times C. Multiply the first row by the second column. 1 times B plus 2 times D. To complete the bottom row, multiply 3 times A plus 4 times C, and then 3 times B plus 4 times D. That is equal to the matrix 6, 3, 19, 2. So again, we have two matrices that are equivalent, and that can only be true if the corresponding elements are equal. So A plus 2C equals 6, B plus 2D equals 3, 3A plus 4C equals 19, and 3B plus 4D equals 2. So I would solve using elimination. I can work with these two equations and eliminate C if I multiply the top row by negative 2. So negative 2A minus 4C equals negative 12, and then copy the bottom row over as is. Combining, I find that A is 7. Once I have A, I can plug that back into either one of these to find C. So I have 7 plus 2C equals 6, which means 2C equals negative 1, and C equals negative 1/2. Solving for B and D, I can use a similar approach. I will multiply the first row by negative 2, therefore eliminating the D's. So I have negative 2B minus 4D equals negative 6. 3B plus 4D equals 2. So B is equal to negative 4. And then, just as I did with A, I'll plug B in to one of the original equations and find D. 2D is 7, So D is 7/2. So then I have my solution. A is 7, B is -4, C is -1/2, and D is 7/2. On the last slide, I just simply represent a system of linear equations as a matrix equation. The elements of the matrix are the coefficients from the system of equations. You can see that the first matrix represents the coefficients of each equation. The subscripts there just identify the row and column in which each element is placed. The second matrix is the variable matrix. And notice again that if you were to multiply the coefficient matrix by the variable matrix and set it equal to the right-hand side of the equation, that would generate the system of equations. So we can solve a system of equations using matrix equations by first writing the system as a matrix. And that concludes section 2.1.